So let's continue on with our discussion on continuity. So we want to identify the type of discontinuity. So the first one, they say f of c is not defined. So there again, they're saying there's no value here. So I can sketch this really quickly. If I were to sketch this at c, I can have a hole there, dear Liza, a hole. At this point right here, well, if I want to say what type of discontinuity, because there is a hole, this is point discontinuity. But I have another one. Like we said, if we have at C an asymptote, there is also no value at C. So this would be, of course, asymptotic. So you can have more than one choice, of course. What about one where the limit does not exist? So let's see here. Well, an easy one would be a jump discontinuity. Mac Daddy make you jump, jump. Crisscross make you jump, jump. So we have a jump discontinuity, or again, at x equals c, we can have an asymptote, asymptotic. Remember, the limit cannot exist at an asymptote. So you have a few choices right there. All right, the next one says, well, what if a function is defined, the limit is defined, but they're not equal to each other? So now I want a value. It might look like a parabola with the hole there at the bottom at C. So it has a limit. The limit exists right here. And then this is the function is defined. So they're talking about the value there. So at C, I have to have a point. So something like this. This is not continuous. And that is because, right, the limit does not equal the value. But that's not the question they want. They want to know what type of discontinuity. So the type is, in this case, a point discontinuity. Why is it a point discontinuity? Because the limit does not equal the value. It's a point because at a small spot, at one point, I can't draw it without lifting my pencil. So now, so if you need to pause, go ahead. So let's take a look at some examples. We're going to identify some discontinuities, the type, removable and not removable, and if we can, write as a simpler problem. I'll give you a hint. If you can write as a simpler problem, this is like that factor cancel method. Okay? So let's try this. So for number 1, I want to find out where the discontinuity is. So in other words, they're saying they don't want no value or limit. That's kind of what they're saying right there, okay? No value or limit. So the only thing we can't do is we can't divide by 0. So for part A, where is the discontinuity? It's x can't equal 3. And again, we cannot divide by 0. No matter how hard we try, we won't be able to divide by 0. And then they want to know, well, what type of discontinuity is it? A couple ways I could do. I can sketch this. Ready? My vertical is at 3. My horizontal is at 1 this time. And if I pick a point, I'm at 0, 2/3. So it's down here. So there it is. Remember I told you only 3 steps to graph any rational function. Vertical, horizontal, and a point. If I let x be 0, it's 2/3, less than 1, so it's below my horizontal this time. So it doesn't really matter. Well, what type is that? Well, there's an asymptote. Clearly, it's asymptotic. I love saying that word. It's asymptotic. And then the third one says, is it removable or not removable? Well, did anything cancel? Please don't do that. I can cancel the x's. They don't do that. Okay, we don't like that. So the answer is no. This is not removable. So because it's not removable, I can't rewrite this. So for part D, we would say not applicable. We can't rewrite it. There's no way I can write it as a simpler problem. All right, for number 2, this is that cool function that you guys did last year. I call it the weird absolute value function. I know it has a name, but I just never remember what it is. At x equals 3, remember? At x equals 3, get rid of the absolute value. This is what it's saying, plus or minus x minus 3. So we have the positive x minus 3 over x minus 3, which gives me a 1. So anything to the right of 3 is 1. But if I pick the negative, Now I get negative x minus 3 over x minus 3, and that gives us negative 1, which is basically says anything to the left is negative. So where is our discontinuity? Of course, it's x equals 3. X can't be 3. What type of discontinuity is it? Jump, jump, crisscross, make ya jump, jump. All right, part C, removable or not removable? We really can't. This is like a yes or no. I mean, it could be a yes, but I kind of say it's not. I guess we can say yes. If you put no, we're okay with that. But if I want to rewrite it, we would get f of x equals plus or minus 1. And it would be, and it's written this way, plus or minus 1 for x not equal to 3, right there. That's basically, you have to redefine it, okay? But if you say no, we're okay with that too. If you say no here, that's fine. It's just that you really can't factor cancel. I guess if you factor out that plus or minus right there. All right, so for part 3, oh no, this is that greatest integer function, the greatest integer function. And I know y'all thinking, Mr. Werner, we have to draw that? No, not really. But just in case you forgot, let's take a look at how it looks. This is the greatest integer function. What it's saying is, if I start at something like 0, 1, 2, we're going to pick the greatest integer that we've already covered. So if I'm at like 0, that is going to be solved because that's the greatest integer. But if I'm at 1/2, the greatest integer I've covered was 0, so anything between 0 and 1 is going to be 0. Anything between 1 and 1/2, well, that's going to put us at 1. Right here. And so on and so forth. So if I want to find out where the discontinuities are, it's pretty easy. It's going to be all integers. That's where those discontinuities are. All integers. What type? No, they're obviously jumps. C, they are not removable. And D, no, we can't rewrite that, okay? We don't even like that. All right, so let's take a look at number 4 here. For number 4, oh, look at this, look at this. On the bottom, I notice I can factor out an x. So I get x plus 5. And notice those are going to cancel. We'll deal with that in a second. So we actually have 2 points of discontinuity. X can't be 0, and x cannot be 5. So let's deal with each one individually. X equals 0 is going to be a whole for us because I could remove it. That's just from pre-cal last year. 5, that's asymptotic because it's going to be our asymptote. And it should be negative 5, not positive 5. Sorry about that. C, x equals 0 is removable because I factored it out. It just canceled away. X equals negative 5, non-removable. And D, yes, we can rewrite this as 1 over x plus 5. That's what that whole factoring provided. X cannot be 0 or negative 5. Just put your domain restrictions. Most people forget about it. That's cool too. All right, let's take a look at number 5. Okay, we're going to sketch. My best thing to do with these is just to sketch them. Honestly, sometimes sketching is just a lot easier to do. And if I were to graph this, if we're saying x is less than 2, this is, remember from pre-cal, this is really saying x is between, is as a distance less than 2 from 0. So we can say x is between negative 2, not including, and 2. So what that says is between negative 2 and 2, we are on the parabola x squared. Has a value of 4 there, right? Looks like this. Oh, it's so cute. It has dimples. Look at that. Now, x is great. Absolute value of x is greater than or equal to 2. This is saying the distance is greater than 2. So this is saying that x is greater than 2 or x is less than or equal to negative 2. So at anything 2 or above, we're on the line 2x minus 1. So let's plug in 2 here. If I plug 2 in here, this is going to give me 4 minus 1, which is 3. Right away. And I know what that line looks like. It looks like this. Let's plug in negative 2. Right away, I can tell it's not going to be continuous here. So plug in the negative 2, I get negative 5. Oh my gosh. That's equal to, so it's going to be solid right there, and it goes down like this. So of course, answering part A, ready? We have two discontinuities. X cannot be plus or minus 2. B, they're the same. They are both jumps. Mac Daddy make you jump, jump. C, they are both non-removable. And D, no, we cannot rewrite that. And the last one for number 6, let's take a look here for number 6. This is our square root. Again, I'm going to graph it. Sometimes seeing something helps. It moves over 1 to the right, and it's our absolute value graph. So for 1, where is this discontinuous? Anything less than or equal to 1. Okay? It's less than because the value does not exist. But what about the equal to part? See, sometimes people say, well, isn't it continuous at 1? The value exists at 1. Anything less than 1, the value does not exist. But at 1, the value exists, so why are we saying it equal to? Well, that's because of the limit. The limit does not exist at x equals 1. And remember, for the reason for that is because the left can't equal the right. You can't equal if you're not there. There is nothing to the left of it. Because there's nothing to the left of here, the limit cannot exist. So for part B, well, what is it? Is it a jump, asymptotal point? Well, in this case, it's none of the above. It just doesn't exist. It's none of those. It just doesn't exist. There's no reason for it. It just does not exist. Unless you get into the imaginary world. It just doesn't exist. That's that fourth one. That's that fourth one I told you about earlier. None of the above. C, this is non-removable. And D, no, I can't rewrite that. Okay, so I'm going to stop here, but I'm also going to do a third video about an introduction to the intermediate value theorem, which is what we're going to talk about next. But I'm going to do a quick little introduction. You can go into the next video if you want to watch that.